I have you loud and clear.
Hello. Welcome. Science.
And that is to say,
physics,
medicine,
nature,
or
space, time,
the brain,
life,
the universe.
Hello, it's science, but not necessarily as we know it. Stay tuned to find out whether you can train your goldfish, whether light weighs anything, and
why can I remember every lyric to every song in every Disney movie, but can't remember which setting to put the oven on?
that's one we can definitely all identify with. I'm Chris Smith, and you're listening to The Naked Scientists.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, with me this week to take on your science questions are Philippe Bougeot, who's a neuroscientist at the University of Cambridge. So what neuroscientific fact have you got for us, Philippe?
Yes, so I came with a big debunking of a myth today because I started teaching in high schools recently, and I realized a lot of people think that, well, actually, we only use 10% of our brain. That is not true. That's the biggest myth we have in neuroscience. And actually, the reason why it's not true is because the brain is extremely efficient. We have nothing in our brain that isn't useful. It's about 2% of our mass in terms of kilos, but it's about 20% of our energy use. So we don't have any space for anything we wouldn't use. And the best example of that is that we're born with about twice as many neurons as we would need. And then they get pruned over time.
There are, of course, just to also be clear, some people who do only use 10% of their brain, but they'll remain nameless.
Exactly. I was going to say, we won't name anyone.
Philippe, thank you very much. Also here, Eleanor Drinkwater. She's been on the show before. You're an animal behavioural expert. You're now at the University of York. So what sort of animals are you looking at?
At the moment, we're studying ants, and in particular, we're trying to understand individual and group level personality in ants.
Personality?
Yes.
Say that again. Ant personality. Are you serious?
They have fabulous personalities.
Really?
Yes, they do.
How do you know that?
One of the ways in which ant personality has been studied is by using RFID tags in order to kind of spy on what they're up to.
These are like when you go into the supermarket, when you walk out with shopping you haven't paid for and the buzzer goes bleep, bleep, bleep.
Yeah.
That's the same thing, isn't it?
Yeah, exactly. Or your swipe card, which you swipe to get into work. It's a similar kind of idea. We can have a setup where we have a RFID scanner and the ant can walk in and out and we can work out who's doing what and how long they're doing it for and those kind of things.
And why have you brought me an empty Petri dish, Eleanor?
So that is an RFID tag.
Where? It's empty. There's nothing in here. Imagine I've taken my biro and put a spot on a page. There is something about that big.
Yep.
So that would go what on an ant? You stick that on an ant?
Yes, with immense amounts of difficulty and patience.
I can imagine, yeah. and some glue. And where do you put the detector then?
So one of the best places is perhaps outside the entrance of an ant nest, and so you can catch them as they're coming in and out of their nests to find out.
The comings and goings of an ant nest?
Exactly.
Oh my goodness, does it work?
It does work, with difficulty. I seem to spend a lot of time gluing tags to ants and then coming back the next day and they've removed them very kindly and put them into piles for me. Yeah.
and are there any ant casualties, or is this a safe experiment? Any biological questions about counting ants and how ants behave? There for Eleanor. Thank you very much. Now, also next to Eleanor is physicist Jess Wade. You've also been on the programme before, and you're a materials scientist. You're at Imperial. You play with interesting materials. You have some interesting material you said you brought with you, wouldn't show me it. What have you got there?
So I've got a little pot of slime here. Any parents in the audience will have heard of slime, will be familiar with its weird material science properties. And this is a particularly weird one because it makes a noise. We wanted something that worked quite well on radio.
You're sticking your finger into the pot.
Can everyone hear it? It's a kind of rude noise, a vulgar noise, I would say.
Is that the slime or is that you?
This is the slime, guys. So slime is an interesting mixture of a polymer, PVA, the stuff that we have in glue, with something called borax, which cross-links the polymer. So we're quite happy with polymers. They're long, wriggly chains, usually of carbon atoms playing around. And they've got these great properties that they're flexible and lightweight, and we can process them. So we use them in my research to make light-emitting diodes. And we use them in plastic bags, and we use them to wrap wires in. But what you can do to them is you can add a tiny amount of something that cross-links the polymer. So it takes all these wiggly spaghetti strands and makes them incredibly straight and rigid. And in slime, we've done that. We've put it in this kind of weird state, which is halfway between a solid and a liquid.
Is that what the borax does?
That's
When you
what
add
the borax does.
It grabs the PVA, which is the glue, and joins the chains together.
Exactly, it does that. And it's kind of interesting because plastic is this big buzzword at the moment after Planet Earth 2. Everyone's really, really concerned about plastic in our oceans, and young people are particularly concerned about it. But yet they're creating all this plastic when they make this slime. You know, they make it, they sell it. And I don't think they're aware that they're actually generating more plastic, which is going to be harder to degrade than they think they're doing. But
So
it's still pretty
you're bursting
fun.
their slime bubble.
Yeah, pop it, kids.
A tiny bit. So that's Jess Wade. Well, sitting next to Jess is another physicist. We're replete with physicists this week, Francesca Day. And Fran, I hear you are a bit of a science comedian. I'm not familiar with many science stand-up routines. Would you like to give us a demo?
Absolutely. So this is a short extract from my Edinburgh Fringe show. I'm a particle physicist. I study particles called axions. They don't, exist as such. So these axions, if they exist, would be zipping through our bodies as we speak, like tiny, ineffectual ghosts. So if they do exist, why haven't we discovered them yet? How hard can it possibly be? They're literally falling on our heads. Well, the trouble with axions is they just don't flipping do anything. They hardly ever interact with normal matter, which makes them very difficult to detect. And in retrospect, a poor choice for the topic of a PhD thesis.
So is that what are you working on? Actually dark matter or something similar? Is that what you do?
Yes.
Because it sounds exactly like you're describing dark matter to me.
Yes, that's absolutely right. Axions are one possible candidate for dark matter.
So this is a sideways dig at your PhD and your PhD supervisor, perhaps?
Yes, one could say that. So in the show, I go on to explain why actually this is perhaps not such a silly idea after all to do this work.
Did it go well at Edinburgh?
Yeah, so I did it in 2016 and that went very well, and I'm doing it again this summer.
Brilliant. Well, we wish you luck with that.
Thank you.
Right, let's jump right in with a question for you, Eleanor. And this is a question from Liz, which intrigues me. I really want to know the answer to this. Liz asks, can I train my goldfish? Can she train a goldfish?
And the answer is yes, you can train your goldfish. I had so much fun researching this question, and it turns out that there are how to train your goldfish kits available online if anyone does want to train their goldfish. And even better, I found out that in the 60s, 70s era of animal behaviour, they were using goldfish as a model to understand what effects alcohol might have on learning. And so they set up an experiment which they tried to teach the goldfish to go into the darkest part of the tank, and they found that adding alcohol to the tank made them learn better. But as is the way with some of these studies, it was unclear as to why this was the case.
Well, goldfish are quite well adapted to booze because they live in, especially in freshwater environments, they live in ponds that freeze over the wintertime. And when they freeze, they run out of oxygen, or they run very low in oxygen, so their metabolism shifts towards the same way yeast. When you grow yeast in the absence of oxygen, you get booze with your grape juice. Well, fish actually make their ponds a little bit alcoholic when the wintertime comes and they freeze in. And I interviewed the scientists who discovered this, and I said, well, could this be a useful way to make alcoholic beverages in the absence of yeast? And he said, well, it would take a very long time. It had about 20 years of a goldfish in the tank to actually make enough. But that might be one reason why that research failed.
Yeah, well, in fact, that's one of my favourite facts about goldfish that you've just come up with. I just love the idea that under stress you start producing ethanol. Can you imagine how much better being stressed would be if that was the case in humans?
Life would improve enormously. Philippe?
Yeah, no, so I was wondering, actually, you're mentioning over winter they have to survive for quite a few months. I, unfortunately, have never had that much luck with goldfish. They've never really survived that long. But I was wondering, how long does it actually take to train them? Because mine, on average, I would say about 4 or 5 months when I was a child. Does it take longer? Does it take a shorter amount of time?
And how do you train them?
Exactly.
Oh, well, the scientific studies in the 60s and 70s, unfortunately, you electrocuted them to train them not to do things. But the nice kits that are available online, it seems to be a bit like clicker training, in which they give them food rewards, which sounds like a much nicer way of doing it than the 60s and 70s way of giving giving them electric shocks.
Because that's a myth. I mean, Philippe was talking about myths earlier and people only using 10% of their brain. People say goldfish have a 5-second memory or something, but actually they have a really, really good memory, don't they? Because people have done research showing that you can train them to find a hole in a net. This is Cullen Brown, I think, from Australia. You can train a fish to find a hole in a net by using various visual cues, and then a year later come back, show them the same net, and they immediately find the hole, so that they've remembered. So they clearly do have very good memories. And if you think fish live a long time, they have to find their way over complex navigations and migrations in some cases, so they must have a pretty good memory. So they ought to be trainable.
Yeah, exactly. I think that fish often get a bad rap just because we can't see them. We tend to think about animals like dogs and cats just because we see them all the time, whereas we don't really see fish. So I think they often get a bad rap in our ranking of how intelligent animals are.
So fish are clever, you'd better believe it.
Can I just temporarily debate that? We put them in tanks so we can look at them all the time. I don't think we don't see them.
No. I'm not saying that we never see fish, but I think that in general, the kind of public awareness of, like for example, if you think about ethics, the ethics of animal, people are very aware of not causing pain to animals. But it was only in the last few years that we proved that fish feel pain, and the fact that that was only discovered like a few years ago is just like mind-boggling, And I think it's perhaps due to the fact that some people are a little bit less connected to fish than perhaps terrestrial animals.
Thank you very much, Eleanor. Fran, here's one for you. It's from Emily, who says, what would you see if you entered a black hole, brackets, and survived, which is pretty important, isn't it? And you looked back through a telescope at the Earth?
So this is a really interesting question. The first thing I want to say is it is actually possible to survive for a short period inside a black hole. So the entrance to the black hole would usually be defined by what we call the event horizon, which is the point where if anything, including light, crosses the event horizon, it can never come out again because the black hole's gravity is too strong. That's why it's called a black hole, isn't it? It's bending space so much that not even light can escape. The light falls into the hole and never comes out again. Yes. So once we cross the event horizon, we're doomed to fall into the black hole. But for all we know, we could be crossing an event horizon of a very large black hole right now, and we wouldn't necessarily feel anything. But if you try to look out of the black hole to other things, for example, the light would be so distorted and bent that you wouldn't really be able to see a clear image of anything outside of the black hole. So if I went in backwards and I'm looking at planet Earth as a blue marble in space in the distance, let's imagine I could see it that clearly. Yeah. As I went over the event horizon of the black hole, because there's still light coming in with me from the Earth, that light would begin to stretch, would it? And I'd see a sort of distorted image. Yeah, it would be warped. The colours would be warped as well because the black hole sort of stretches the light. So the answer to the question then is you would see it, but you wouldn't see it clearly? Yes. Philippe?
So would it be a bit like, going back to the goldfish, a goldfish looking at us through air?
Yeah, maybe. That's nice how it all links up, isn't it?
Exactly.
Anyone would think someone put this show together. Now, while you're there, Philippe, actually, we've got this question, which is for you from Marika. Have a listen to this.
What is a déjà vu? How does that happen in the brain?
Now, haven't we had that question before? Or is that just my imagination? Boom. Yeah.
I've had that question a few times. Actually, unfortunately, I can't give you a 100% certain answer because we still don't know what a déjà vu actually is. We have a few theories, though, and that involves a lot of the memory circuits. The hippocampus is involved in encoding the context in which memories are formed. But right next to that, there is a part of the cortex called the rhinal cortex. And that rhinal cortex is divided, but its main role would be to recognize what's familiar. And so one of the big theories at the moment is that this rhinal cortex needs to fire in line with the hippocampus, which encodes context, and then that opens up a memory. So it'll fire the network that's associated with a specific memory. If, unfortunately, you don't have that context firing, you just have that feeling of familiarity, then that might be why you have a déjà vu. So we're not sure. The only real studies that have been done into that are starting to show us that that's the case. There's stimulation of these parts of the brain that also seem to create fake déjà vus, if you want. But we still don't know why it would happen. It seems to happen more in young people, or it might just be that young people are more aware of it because we still have a lot of our brain intact because aging hasn't started.
Happens to me when I'm tired. Does that make a difference?
Yes. So stress and fatigue actually are huge links to more déjà vu experiences.
I suddenly have a sort of flash of recollection and a feeling that oh, I've thought of this before, and it's a memory that's fleeting, and it's there and then it's gone, and I can't get it back. But it only happens when I'm really tired, after night shifts and things. When I was sort of junior doctor, it used to happen quite a bit.
Yeah, exactly. So that's probably when it would happen, especially for undergrads, actually. I think it's something like 2/3 of undergrads seem to have experienced a déjà vu feeling. So
don't remind me. Fran?
So I used to be absolutely convinced when I was 7 or 8 that a déjà vu was something that I'd dreamt, but I'd forgotten the dream. So I was sort of remembering from a dream. Is that at all plausible?
Oh, I wish I could give you an answer. I don't actually know. I would not think so, because our brain seems to be very adapted to not remember our dreams. Otherwise, we would have a lot of issues functioning in daily life. You already have to remember what's happening for 12 to 16 hours every day. If you have to remember everything that's happened overnight also, that would be a big issue.
There are some people that do, though, aren't there? These people who have some kind of savantic behaviour and can remember in excruciating episodic detail everything that's happened to them throughout their lives.
Yes, so it does happen for some people. That is fortunately not the norm, because it is, like you said, excruciating for these people. But it happened in some cases. I wouldn't be able to tell you why it happens, but it does happen, yes.
Thank you, Philippe.
So what we were trying to do with this paper is to demonstrate the ability to type using brain signals, anywhere between approximately 4 and approximately 8 words per minute, a factor of between 2 and 4 faster than what's been demonstrated before.
Each month, the eLife podcast talks to some of the world's best scientists. Join me, Chris Smith, as I hear about breathtaking discoveries hot off the press. Find the eLife podcast on iTunes or listen and download for free from nakedscientist.com/elife.
You're listening to The Naked Scientists with me, Chris Smith, joined this week by a panel of experts because we're answering the science questions that you have been sending in. Still to come, why do bees die when they sting you? Wasps don't, though. Why do we get irritable when we get hungry? And why do some metals appear to corrode or rust faster than others? Meanwhile, if you'd like to get a question into a show like this, then you can send them in by email. It's chris@thenakedscientist.com. You can also track us down on Facebook. That's facebook.com/thenakedscientists. Or you can tweet @nakedscientists. I just want to ask everyone, did anyone catch the news recently that NASA think that they have got the best evidence yet that there may have been life on Mars, or at least they think they've found food for aliens? Did you see this paper in Science?
Yeah.
With the Curiosity mission, which has found this interesting material.
Yeah, so I saw it. I'm hoping you guys all did too. So NASA reported that they've actually found these organic small molecules on the surface of Mars. And this is kind of crazily exciting because Mars has incredibly strong radiation. They have a really, really thin atmosphere for whatever reasons. They don't have a magnetic field, interestingly, and that could be that is the cause of their very thin atmosphere. So they're being bombarded by particles from the sun and cosmic rays from space. And what you wouldn't expect in that kind of situation is for there to be any kind of organic material that could possibly survive. And Curiosity went up a long, long time ago. And it can only see so far. Curiosity can only dig about 5 centimeters of the surface of Mars. So it's particularly exciting that within that 5 centimeters, you have these organic materials. And kind of the future of space travel to Mars, in 2020, there are going to be 3 big missions. NASA, ESA, and China are going up. And the ESA drill, the European Space Agency one, can drill 2 meters into the surface of Mars. So everything we saw in this kind of 5 centimeters, whoa, crazy exciting, this is mind-blowing. But imagine what we can see 2 meters further down where this radiation doesn't hit. And that's just so cool.
Philippe?
So going back to the 2 meters down, did it be possible basically that the tiny particles they found now would be particles that were much bigger and got degraded over time, so more complex organic molecules?
Yeah, it could be. I mean, these are kind of little segments of organic materials that we're really interested in. I guess looking further down, we're interested in what kind of rocks are there and how similar they are to ones that are on Earth. But certainly the kind of science payload of all of these missions is so cool, right? So they drill down, they collect this tiny amount of material, they take it into what looks to us like an egg box. And then in there, they have a Raman spectrometer, they can do mass spectroscopy, they can do all these crazily precise measurements to work out exactly what that is. And the funniest thing is there was a boy during my PhD doing a PhD with me, and he was looking at one particular small molecule, one particular part of a polymer. And the whole time he was looking at this and we were like, you are so boring, like get a new material, that's the most boring thing ever. And now he's working at NASA at the Jet Propulsion Lab programming for the new Mars rover, and this particular molecule is the one they found. So it's just so funny that it's like coming home.
He's very jealous. Everyone's very jealous of him now. Right, on to our next question, which is for you, Jess, and it's from Deirdre.
How do lasers work?
Ooh, this is a great question, Deirdre. So everyone loves lasers, right? Along with slime, they're the second best thing in physics. So lasers work because we have atoms, and inside an atom are some protons and neutrons, which is what Fran studies. We're more interested in the electrons in material science. And what we need to do is, in a laser, is we need to excite one of these little electrons up to a kind of excited state, we call it, but it's really unstable in this excited state. It's like you give a child loads of slime to play with and they suddenly go ferociously energetic. And then really quickly it needs to stabilize, so emit some light to get back down to its ground state. And you can do a really clever thing where you trap loads of atoms together so that when that one little electron jumps down and emits its light, it excites another electron that's nearby it and makes that emit its light also. And you have this kind of cascade effect where it keeps happening. And you can do that by trapping these atoms between mirrors or something clever. And what's really exciting about laser light and why physicists like it so much is that little jump that the electron makes, that energy that it gives out is really specific to the atoms that you're exciting. So laser light is only one color, it's only one energy. And that lets us do all kinds of clever physics because then we can use that laser light to excite different atoms which absorb that particular energy. And it's also super focused. You know, you get these laser beams. You have a light bulb that gives out this really diffuse light, but laser beams come at you super focused, and we can keep them focused for a very, very long time.
And of course, by using different flavours of atoms, you can get different colours of light that have different applications, because if you want to do, say, medical imaging or you want to burn bits of tissue, you want a laser that will interact very well with tissue, but not other things.
Exactly. And it's very similar to fluorescence. So fluorescence is this thing where we excite an atom and very quickly they emit light, and it happens over a very short timescale. And when it happens, it's gone. And you can tune that fluorescence, you can tune that colour to whatever atoms that you're exciting.
Eleanor.
So, talking of applications, something I've always wondered about lasers, taking this to a really highbrow level. I love Star Wars, and you know, one of the weapons that they use is these kind of laser shooters. Is that ever going to be possible? Having kind of weapons that are lasers?
Do you have nefarious intent or something?
Oh, of course not. I don't know why you suggest that.
When working with the ants becomes too much.
Well, you know,
it's gone from burning them with a magnifying glass to
I would never
a laser
do
blaster.
That.
Jess, laser blasters.
I don't think I mean, if you wanted a laser blaster, you can make a laser blaster, right? You'd get a very powerful laser. You could fire it at something. You can pop balloons with certain lasers. You could certainly blind yourself with a laser. I mean, the majority of time spent at the beginning of your PhD in materials is trying to complete laser safety courses so you don't blind any of your friends with a laser. So I don't think you're far off the Star Wars thing if you want one.
Jess, thank you very much. Philippe, can you help us with this question in which we all sympathise? I think we've all had this. V wants to know the following.
Why do I turn into an inhumane monster when I'm hungry?
Why indeed?
Well, V, that can be explained with science. Actually, the explanation is quite simple. When you get hungry, your glucose level in your blood goes what your brain would consider dangerously low. It doesn't take much to reach that level because your brain, like I said earlier, actually uses about 20% of your energy demand every day. So as soon as it senses lower blood glucose levels, it starts to release the same hormones that you would get when you're angry, anxious, or stressed. So cortisol, adrenaline get released at the same time. And these are surprisingly, or not surprisingly in this case, the same neuropeptides or neurotransmitters that are associated with anger. So there is actually a scientific reason for people becoming hangry, if you want. And fun fact, it's actually worse for men. So usually the stereotype would be that, everybody gets angry. But actually men have more of these receptors. So even though they might not show it, it actually affects men more.
And so the cure is an easy remedy. Eat something.
Exactly. Yes. No, for sure.
And are some foods better than others? Because sugar is very rapidly absorbed, isn't it? So is that the best cure for hunger-induced crankiness, or
for me, I would go with chocolate.
Eleanor's laughing.
I'm not sure it works for everybody, but yes, you want to get that blood sugar level really high really quickly. You don't want to crash, however. So the solution I found is just keep eating
more chocolate.
Exactly.
Yeah.
Never stop.
Right. That'll sort you out. Thank you, Philippe. Jess, time for a question for you.
Why do some metals rust faster than others?
That's from Val. What do you think? Why do some things go rustier?
So the technical term, I think, is corrode. Rust, we really only think about iron. So iron rusts and goes that typical kind of rusty bronze colour. So that's all right. And corrode is when metals interact with oxygen, usually in the presence of water. And it's because oxygen is super reactive, the oxygen that's in the air. It's a really hungry little gas. It needs to fill 2 electron spaces. So it attacks these metals, which are kind of seas of electrons, and tries to pull them off that to react with it. And some metals, this seems to happen very quickly, so in things like iron. The interesting ones are the things where it doesn't happen. And aluminium, actually, super quickly, aluminium that we use in cans and in an awful lot of products, covers itself with a very, very strong layer of aluminium oxide. So that makes it look like it's not rusted. But that layer is super tough and sturdy, and no more oxygen can get through it. So we can do that. We can do other kind of clever things with metals where we blend them with other metals to stop them from corroding. I think the ones that are really interesting are things like gold and platinum, which have this sea of electrons. You know, gold is really good at conducting electricity, which is why we use it so often. And it's beautiful if you buy expensive jewellery. But that doesn't seem to rust. So the kind of interesting questions are why is that not happening? And I think that's much, much more complicated than we think. It's a kind of, quantum chemistry question why it doesn't happen in gold. But certainly all metals do seem to rust. They want to get back to their kind of state that we found them in these mountains in when we started refining them in the first place. So it's a rate. You can look at a table to see which will rust faster.
You can make gold dissolve, but you need a mixture of all of the 3 sort of king acids, don't you? Nitric, sulfuric and hydrochloric acid. Aqua regia, I think, isn't it, to dissolve gold, and it's pretty horrible stuff.
Yeah, I don't advise doing that at home.
No, probably not a good idea.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
You're listening to The Naked Scientists with me, Chris Smith, and I'm joined by physicist Fran Day, animal expert Eleanor Drinkwater, another physicist, and that's Jess Wade, and a neuroscientist, Philippe Bougeot. And we're answering your science questions. If you'd like to send one in, it's chris@thenakedscientists.com. Now, before we continue with your questions from people at home, we'll first of all ask some questions of our panel here that we wrote earlier to test their mettle. So we'll have 2 teams. Philip and Jess, you're going to be Team 1, and Eleanor and Fran, you're going to be Team 2. Now, because it is a World Cup year, we're feeling pretty sporty, so we've got some speedy-inspired questions to kick off with. Did you see what I did there? Right, Team 1, Philippe and Jess. Talking of round ball-shaped things, there's the sport link. Planets. Which goes by more quickly, a day on Venus or a year on Mercury? What do you think?
You're the physicist, so I'll trust you on this one.
What's shorter?
You can take it?
No.
Okay, let's go with a year on Mercury.
You're going with a year on Mercury. You get a bing for that one. That's indeed right. A day on Venus is 116 Earth days long, but a year on Mercury is just 88 Earth days. Venus turns very slowly.
Cute.
Right, +1 for Team 1. On to Team 2. Eleanor and Fran, which is happening faster, the growth of Mount Everest or the separation of the Earth from the Moon?
Ooh, blimey.
That is a great question, which I've never thought of before.
I have no idea.
Well, we can get
Mount Everest. I don't even know if Mount Everest is growing. Is it growing?
Yeah, I think it's growing.
Okay.
Yes, it's growing. I'm gonna go with Mount Everest.
Yeah, my instinct is Everest. Mount Everest.
Okay, going for Everest.
Oh.
I'm very sorry to burst your bubble, but in fact, it's the Moon. Everest is growing by 4 millimetres a year. The Earth and the Moon are separating by 4 centimetres a year. And that's because the Moon is gaining angular momentum from the Earth. Because the Moon is going round the Earth and the Earth is turning inside the Moon, that's why we have tides, of course, because the water on the Earth is being attracted by the Moon. But because the Earth is turning inside the orbit of the Moon, that bulge of water on the surface of the Earth close to the Moon is slightly ahead of the position of the Moon in its orbit, and it's dragging the Moon round with it, giving some of the Earth's spin energy to the Moon, accelerating the Moon, so the Moon is therefore moving further away from the Earth progressively by up to 4 centimetres a year. And we know that because of a laser, which Jess told us about earlier, which is being bounced off a mirror which is on the Moon's surface, put there by the Apollo missions. Or if you believe the conspiracy theory, it just got there. Team 1, so you're in the lead at the moment, Team 1. Which is faster, Usain Bolt or an African elephant? You can even try what happens if Usain Bolt is chased by an African elephant, if you want to consider the question in a slightly different way.
I was going to say, that might change the answer, though.
It doesn't, does it, in the grand scheme of things? But, unless he gets caught.
Okay.
I have seen many documentaries of elephants running.
I've seen Usain Bolt running, and he's very fast.
He is extremely fast.
You choose. You're the elephant expert.
Well, I mean, we've never seen...
He's a neuroscientist, isn't he?
Well, I can tell you from their cortex that it's quite heavy.
Their brain.
So they might go a bit slower than Usain Bolt, who has a smaller brain to carry around. So I'll go with that neuroscience answer.
Okay.
If I'm honest, I don't think it's the brain that's the major mass contribution in an elephant.
Let's go with Bolt. Let's go with Bolt.
You're going with Usain Bolt. Okay, here we go. You are correct. Elephants can manage 25 kilometres per hour, but Usain Bolt has been clocked at over 47 kilometres per hour. So, team one, you're streaking into the lead. Okay, let's see what happens with Eleanor and Fran now. Which moves faster, the electrons in a wire or an F-18 jet?
Ooh. So, by the electrons in a wire, that's quite a complicated question.
I know, you're on a complicated show.
They're not really just zipping through the wire. They're sort of bumping into each other and there's sort of pseudo-particle motion.
So what are you going to go for? Which do you think goes faster? Is it the electrons or is it the jet?
My instinct is the jet. It's going to be very embarrassing if I'm wrong on this. What do you think?
I bow to your superior knowledge of electrons.
It sounds to me like you're going for the F-18.
It's a lot of subtleties that make the question harder. I do not know the answer. I'm going for the jet.
Yep, it is the F-18. You are quite right. Good to go with your instincts. Always trust your instincts. F-18s can do 1,915 kilometres an hour or thereabouts, but the speed of individual electrons in a wire is just 0.2 millimetres per second. Now, an electrical signal moves along a cable at almost the speed of light. That's absolutely true, but the individual electrons that carry the current are actually moving very slowly, and that's because electricity moves along a cable a bit like if you had a tube full of beads and you pushed in a bead, an electron at one end, it shunts along all the other beads inside the tube, so another one comes out the end, but the individual beads, the electrons, move incredibly slowly, so that's why it's only about 0.2 millimetres a second. So it's 2-1, and let's see what happens on the final round here. Team 1, back to you. If you could drive vertically at motorway speeds and in a straight line, which would you reach first, space or the deepest point of the ocean? What do you think?
Oh, definitely space.
Yeah, let's do it. I can't drive, so over to your superior knowledge.
Let me just get this right. You reckon that driving at motorway speed vertically, either up or down, you're gonna get to space before you get to the bottom of the ocean? That's what you're saying, yep?
Let's do a clever kind of Fran way of answering this. It depends where you define where space begins. But yeah.
Where do you start also is a good...
I'm pretty sure. I'm going to go with I agree with you. The International Space Station is closer to us than Glasgow, right? So I think we could go with that.
Okay, you're going to go with...
Let's go with
space.
Oh.
No, you're not right. Actually, you'd reach the ocean floor first. And this is because the edge of space is about 100 kilometres above the surface of the Earth by our definition of where space starts. The Mariana Trench in the Pacific is, in comparison, 11 kilometres deep. So you'd get there a lot quicker. The International Space Station about 400 kilometres up, Jess. So it's, Glasgow's a little tiny bit further than that, but yeah. So you didn't get that one right. So now it's all on you guys, Eleanor and Fran, to see if you're going to manage to equalise, which will push it to a tie-break situation. What unit of this is nasty? Okay, I'll give you this. Nasty, this one. Which unit of time happens faster, a shake or a jiffy?
Can we answer the elephant questions? A shake or a jiffy?
I was unaware that either of those were actually defined units.
Depends what you're shaking, because you say 2 shakes of a lamb's tail, what maybe it's another type of animal.
Yeah, I don't know at all. A jiffy sounds quicker,
yeah.
Just a jiffy, whereas a shake, maybe I like to shake for a long time.
Okay, let's go with jiffy.
You're going with a jiffy?
Yeah.
You're going with a jiffy?
No!
Did you know that, Jess? You had your hand up.
No, I had my hand up because I liked the look of the Canadian while that was happening. He was like, what is a shake? What is a jiffy?
Not a milkshake. A shake, actually, is a top secret unit which was coined for the Manhattan Project. A shake is 10 billionths of a second. A jiffy is used in computing engineering, and it's 100th of a second. In other parlance, an eye blink is about 10 jiffies, or roughly 10 million shakes. So, you've got 0 for that one. So I think that was, therefore, Jess's team, you have it, don't you? I think you got 2. So unfortunately, Eleanor and Fran, you didn't win this week. So the big brains this week, Philippe and Jess, with their amazing knowledge of elephants and Usain Bolt running. Very well done. Right, back to the questions. Eleanor, bees and wasps are out in the UK at the moment, and in fact we found a very large hornet in the Naked Scientist's office the other day. James wants to know the following, please.
Why do bees die when they sting you, but wasps don't?
This is a really good question. I recently started beekeeping, so this is a question that we've been particularly interested in. But the answer...
Your bees faring better than your ants.
Yes, they're doing marvellously.
You're putting RFID tags on them and squishing them.
No. We're looking after them brilliantly. They're doing really well. They're excellent. I'm very proud of them all.
So be proud of you.
Yeah, exactly. But they are amazing. And so what you're talking about is the fact that honeybees in particular, there's many types of bees, but I'm guessing that in this case we're talking about honeybees. They have a barbed sting. So if they sting something like a mammal that's got nice fibrous tissue, then they will actually pull out if they stick their barb in, it will get stuck. And so then if the bee is removed quickly, then it will pull out the sting and then quite a lot of associated tissue as well. So they effectively disembowel themselves, which is quite sad. But the amazing thing about it is they can still live to, I think the study said, up to 114 hours after effectively disemboweling themselves.
Why have they evolved to do that, though?
Now,
because Australian native bees don't have barbs. They're stingless.
Yeah.
They're barbless.
Yeah. So this is the honeybees in particular. Now, I was reading about this to try and answer this question because I thought that might come up. And there seems to be 2 different schools of thought, one of which is suggesting that perhaps it's maladaptive and it's just that it was evolved to sting other insects which don't have the fibrous tissues like we have. The other school of thought, which I think I'd prefer, is the idea that if they have the sting in longer, then it causes maximum amount of damage to the mammal because the whole time it's pumping the venom into the mammal. And so essentially the worker is sacrificing herself for the colony. And then the fact that they can survive up to 114 hours after, they can still participate and help defend the colony. So
it's all in the name of better persuasion against nest raiding.
Well, that's one hypothesis. Obviously, it's quite hard to tell the difference between the 2.
You may not know this, but do furry animals fare better? As in, do bees manage to find it harder to sting things like dogs and bears and things that might go after their nests? Because they go for the exposed parts on us. But my brother, who keeps bees, told me that when his bees get into your hair, because we watched a swarm arrive at a capture hive he'd set up the other day, and we had them all buzzing around us. He said, just watch out if they get in your hair, because they tend to panic when they get in your hair, and then they just sting you. And none did sting us, but do furry things fare better? Or fur better?
I don't know. Well, I would guess it probably depend on the type of fur. Because I guess if you could get, like our hair, if you get tangled in it, you'd have someone panicking. But I would wonder whether on other animals the fur is kind of thick enough that you can't sting through, like us wearing our beekeeping suits.
Who knows? We'll have to leave that one for another day. Thank you very much. Jess, can you help Katie out with this one, please?
Does light weigh anything?
Does light have a mass?
Yeah, this is great. So I think firstly we need to think about light in 2 ways. So we need to think about it as it being a wave, which we're all quite happy with, which reflects and kind of bounces off things and diffracts and gives us great colours. And then we also need to think about it as being a particle. And this is quite complicated, and it comes from some great work done at the beginning of the 1900s to show that light comes to us as these tiny little packets of energy called photons. And photons move in waves, and that's exciting. But these photons we define in physics, and I hope Fran agrees with me, we define that photons have no mass, right? Yes. So photons don't have any mass, but they're travelling incredibly quickly at, unsurprisingly, the speed of light.
Is that why we say they have no mass? Because they couldn't travel at the speed of light? They wouldn't have enough energy because it would take an infinite amount of energy to travel at the speed of light if they weighed anything.
Exactly that. And it helps us out with an awful lot of equations that photons don't have any mass.
So is it a fudge? Or is that really
tricky,
the case?
Well, I think the thing that makes everyone think it's, photons should have mass is we always say E equals mc squared, right? And photons have this phenomenal amount of energy, E. So therefore they should have some tiny amount of this m to give them this thing. But what we're not actually thinking about is E equals mc squared only really holds when you have no momentum. So E equals mc squared holds in an invariant frame when the momentum is 0. So in a photon's case, all of its energy is coming from its momentum. And that gets us round, whether you think it's fudging or not. What we can say, and what I think Fran might chip in with, is photons behave like they have mass. So photons do Am I right?
They can give things a push, can't they? Because there's this YORP, the Yarkovsky-O'Keefe-Radzievsky Padak effect, where light hits things.
Classic.
And,
Classic effect.
Yeah, well, it's well known. It pushes asteroids around in the solar system and probably dislodged the asteroid that did for the dinosaurs by giving them a nudge, because that light falling on things gives them a push.
Yeah, so they have a momentum, but they don't have mass, which in general relativity is possible. And I was just going to chip in on the is it a fudge question. People actually do experiments to try to work out if the photon might actually have a really, really tiny mass, because you can never rule out maybe it's got a mass that's just like 1 billion billionth of the mass of an electron or something. I think the limit is lower than that now. And the limits are very, very small at this stage.
It sounds like the beginning of your PhD. Like, it's this particle. We don't think it exists. Go and have fun for 4 years.
It literally is in the beginning of my PhD.
Thank you, Jess. You're listening to The Naked Scientists with me, Chris Smith. Still to come, the weirdness that is quantum mechanics and what is quantum entanglement. How do trees get water when they're being concreted into position, for example? And what is dark matter? Dan wants to know, what is quantum entanglement? Can we create it and how does it work? But you better tell us first actually what quantum is.
So quantum mechanics describes the physics of how very small things work. And it turns out that the physics of how very small things work is super weird and nothing like the physics of how everyday objects work. And one important point is that in quantum mechanics, nothing is decided until we measure it.
Can I just clarify, when you say really small stuff, how small is really small?
So the size of an atom or an electron or a proton, which are the particles that are in atoms.
Does that mean then if I could, with a microscope, start with something big and watch how it behaves and get smaller and smaller and smaller and see progressively smaller things, I would suddenly at some point see the behaviour switching and going into this quantum realm where things behave totally differently than bigger objects?
That's a very interesting question, whether you could do it gradually. No one quite knows how the transition from quantum to classical physics works. It's one of the really open mysteries, because there isn't a microscope that can do that whole range.
So the quantum mechanics has thought of that and caught us out.
Yes, quantum mechanics is very good at doing that kind of little trick.
Niels Bohr said, if you're not baffled by it, you didn't understand it, didn't he? He's saying, look, I understand how it works, I understand the results I get, but I don't understand why I get.
That's absolutely right. Quantum mechanics is a set of rules that's very, very good at predicting the results of experiments. So you sort of have to go with it.
And just abandon all hope of actually understanding why. You just know it works.
We haven't abandoned all hope. There's a lot of scientists working on it.
OK, so coming back to this idea of entanglement, what's that?
As I said, we don't decide things in quantum mechanics until we measure them. So, for example, photons, which are particles of light, have a property called polarization, and that describes the direction their electric field points in. And before we measure the polarization of a photon, even the photon itself doesn't know its polarization. Now, it's possible in an experiment to have, say, an atom emit 2 photons at once, such that they have to have their polarizations pointing in opposite directions. When we do this, and say the photons travel to opposite ends of the world, and then we measure one of them, and it's pointing in a particular direction, then we measure the other photon and its polarization will always be pointing in the opposite direction, because those 2 photons are then entangled. And this happens instantaneously. So it's very mysterious how the information can travel from our measurement of one photon instantaneously to our measurement of the other photon.
Now, is it that the entanglement, the decision as to what polarity you're going to have, that decision is made at the moment the 2 photons leave the atom? Or is that decision made only at the time when you measure one of them?
It's made only at the time when you measure one of them.
And how do you know that?
From the experiment I've described, there isn't a way of knowing that. So you might think, well, why isn't it just decided at the source? But there are actually more complicated experiments you can do involving measuring things at different angles and doing lots of different measurements that show that it has to be decided only at the point of measurement. They're called Bell inequalities, if anyone wants to Google further.
And over what sorts of scales can this operate? Or is it infinite? As in, if I had a particle which was generated at the time of the Big Bang and another particle, its pair, they're now on opposite sides of the universe. As far as we know, does the same rule apply?
Yes, as far as we know, it is infinite. However, when I say a measurement, something like the photon interacting with a few other particles, interacting with its environment, can destroy the entanglement. So you'd have to really isolate your photon somehow as it travelled across the universe.
But that also means that there is in some way information travelling over vast distances in zero time for this to hold. So how on earth is that happening?
We don't know. It seems like it's in conflict with Einstein's theories, which say that things can only travel at the speed of light, not infinitely fast. It's actually possible to prove that it's not possible to communicate this way in a way that violates Einstein's theories. But it's still very mysterious and people spend a long time worrying about it.
It certainly is, but it could hold the key to, well, it does hold the key to information protection, doesn't it? Because basically it's a fail-safe way of knowing if information's been tampered with. If you entangle some information in this way and you've read one bit of information, it will change the other, so you can tell. And that's how online security works, isn't it?
Yeah, so people are very interested in this for security purposes. It's a lot better than anything you can do classically because it's literally tamper-proof from the very laws of physics themselves.
Thank you, Fran. Philly, here's a question which I love from Nat.
Why can I remember every lyric to every song in every Disney movie, but can't remember which setting to put the oven on?
I think we all have this problem, don't we?
I was going to say, I think I sang Let It Go all morning, actually. Yes, that is a common problem that people have. And actually, it's something that's really great for humans because until quite recently, we didn't have written language, right? So songs would have been a really good way to transmit information. And there's a really good reason why they are so good. Memories are a bit like networks. You can think of them in the brain as different neurons linking and showing specific patterns. So two similar memories might have similar patterns, but differ on like a few final roads, if you want. And what happens is that a lot of these networks, the more neurons are involved, the easier it is to remember something. So while your oven might only have a specific network, so you can think of the network as like a tree, and you would have a trunk, and you can't think of the trunk, what happens with other memories is that you would have multiple trunks going into that memory. So in music, you have rhythms, you have what you were feeling when you were listening to it. You have what was happening when you were younger. So all of these things happen, and at the same time, you're happy. And you always try to reward yourselves with things that make you happy. So your brain will try to make you remember these things much more.
The ancient Greeks, for example, and the Romans, Latin classicists, had poetry. And I put this to a classicist and said, is that why poetry and the rules of the language became so rigid and were rigidly imposed? Because if you have a rule to go by, then you have to make the language fit the rule, and then it helps you to remember, because you're remembering what the rule should be. You make the words fit that rule, and therefore it's easier to remember what the message should be, so you don't distort your message.
Exactly, and rhymes are a really good thing for this. Actually, there was a study done recently on can you remember more textbook information if you make it rhyme? And there's a reason for yes, the answer. Basically, you know what the rhymes... No, you know what the rhyme's going to be. So you know what the rhyme's going to be, so your network is activating. You already know that the sentence is going to end with ing, for example, so you can fill that in with the rest of the information you have in your brain. So it's actually quite clever, and song is probably the best way to remember things.
And are there then mathematical formulas to create a song that has the most lasting impact on our memory? Can you, I know this word earworm, is that right? You make a pop song that's really, really, people are going to like hearing it, and then you sell them.
But it might be memorable for all the wrong reasons, and actually more comes into it. You might hate it so much.
Exactly. Two things that can make you remember a song a lot more on that front. If you really like it, you'll remember it a lot. If you hate it, you will also remember it a lot.
Yeah, we've had that.
Yeah, because you're getting a lot of emotions involved. As for the perfect song, so I know there's a lot of machine learning techniques being used at the moment to try and compose fake songs or songs that are not created by humans. I don't know how that's going, but pretty much every pop song uses the exact same 4 chords. And that's, well, there's a reason for that. We keep remembering them a lot better. So it's a lot easier to sing, let's say, Rihanna than sing some Frank Sinatra. I'm saying that. They might use the same 4 chords, but for me, I can't remember.
You should make that rhyme.
I should really try. But yeah, so basically songs that you hear a lot more, you will remember. So even though there's no necessarily perfect formula, although there might be right now, I just don't know that field enough. Well, you might remember things that you hear more in public. So when you're listening to the radio, you have that.
Thank you, Philip. Fran, time for a question for you, which is from Adam.
Is dark matter definitely there? Is it just a neat idea that explains strange things about the universe, or is there direct evidence?
Fran, what do you think?
So first I should quickly explain what dark matter is in case anyone doesn't know. Dark matter is matter that we think is there because we can see the effects of its gravity on other matter, like stars and galaxies in space. But we haven't detected it any other way than its gravitational effects. So then you might think, well, maybe it's not that there's extra matter. Maybe we just haven't quite understood gravity. And indeed, there are physicists that work on modified gravity as an alternative to dark matter.
What's modified gravity?
It's where you take Newton's laws of gravity, or even Einstein's theory of gravity, and you tweak it to try to fit the observations better.
That's called fiddling, isn't it? Isn't that called
Yes.
kind of add in a fiddle factor to make the observation,
Yes.
fit the facts?
Absolutely.
Sounds iffy to me.
So dark matter is much, much more popular because based on just having one more particle in our model of particle physics and having there be some of these particles around, we can explain all the observations. But there are observations that dark matter can explain very easily, but modified gravity can't. For example, dark matter is required to explain how structures like galaxies form in the universe in the first place. You need the gravity of the dark matter to be the seed that holds the galaxies together, whereas modified gravity can't explain this. So dark matter really explains a lot of different astrophysical observations with only one addition, which is what makes it a very appealing theory. But of course, until we detect it, we can't know for sure.
Why would all the dark matter stick together and be in a big halo around a galaxy, for example? Because if it's gravitationally active, why isn't it all sort of mixed up with the other material we have, the stars and the planets and so on?
So it is, but it's more the case that the stars and the planets are mixed up with the dark matter. So we think that dark matter probably only interacts significantly via gravity, and its other interactions are very weak. So the dark matter falls in on itself because it's gravitationally attracted to the other dark matter and forms these big blobs of dark matter.
So dark matter is attracted by gravity to other dark matter, but it doesn't interact with dark matter in any special way, apart from via gravity, we think.
We think it might interact with other dark matter using some other forces that we don't know about yet, but there's no direct evidence for that.
And we think it was there, as a product of the Big Bang? Has it been around since the birth of the universe?
Yes. So in the same way that all the regular matter that we see every day was produced in the Big Bang, dark matter would also be produced in the Big Bang at the same time.
So when scientists talk about there being particles of dark matter whizzing through us all the time, one physicist at UCL in London put it to me that, if I had a pint glass, I'd have at least a couple of dark matter particles in there right now. Why is that there? Why isn't it out aggregated around with the dark matter in a halo then? I mean, is that just a reflection on how much dark matter there is all over the place all the time?
Yeah, so it's best to think of the Earth as being in a dark matter halo. So the Earth is situated in the Milky Way galaxy, and the Milky Way galaxy is situated in a big sphere of dark matter. So because we're in this big sphere of dark matter, there are dark matter particles around everywhere.
And so will the dark matter go where the matter goes? Is that why we've got our galaxy, there's a mixture of matter and dark matter in the same place in space and time?
They're gravitationally attracted to each other. But it's better to think of it as the matter going where the dark matter is.
Philippe?
Because dark matter is then a form of matter, would there be something as an anti-dark matter particle?
That's a very interesting question. So in some theories of dark matter, there is anti-dark matter particles, but in some theories there aren't. So in the same way that an electron has an antiparticle, which we call the positron, but a photon is its own antiparticle. It doesn't have a different antiparticle. It's the same for dark matter. So some dark matter wouldn't have an antiparticle, but some could.
Thank you very much for shedding some light on dark matter. Really, really lucid and clear explanation. Thank you, Fran. Now, can you help out Les, please, Eleanor, who's wondering about trees that you see living in cities? And he points out that when you have a tree living on a city street, often concreted into position. The tree seems to be doing quite nicely, thank you. So how's it coming by its water and its nutrients, he wonders?
Well, that is a really good question. Trees, plants in general, can be amazing in adapting how they grow to the different environments in which they are. So you can think about something like a willow tree, and if you plant it by a river, it might not put down very strong roots because the water's right there. So it can be a problem with willow trees that they might flop over because they just don't have the support structure there. So perhaps with the trees that you're talking about, they have much more in-depth root structures that's adapted to the environment so they can spread out and find what they need.
Do you think it also could be a factor that if you have concreted over the ground, actually what you're doing by doing that is trapping water in the ground?
Yeah.
Because the sun's not hitting the Earth's surface and therefore evaporating water. So the Earth might be losing a bit less water, so the tree might not actually have to try so hard to get at ground resources as it normally would. There's less competition and there's less evaporation.
Yeah, that's a very good point.
I mean, in my experience, lots of trees that are grown in that way end up solving the problem for themselves by basically turning the pavement into a trip hazard, don't they? And you just get this massive load of dislodged paving stones and the tree says, I don't care, I'll get these out of the way. Because it's testimony to the power of water, really, isn't it? Because these trees grow and then they're using water, sort of hydraulic pressure to split rocks and concrete out of the way so the tree can grow. So, thank you, Eleanor. And on that note, we must leave it there because we have run out of time. Thank you very much to our guests, Fran Day, Philippe Bougeot, Eleanor Drinkwater and Jess Wade. Georgia Mills and Katie Haylor put the programme together. Do join us next week when we're going to be getting to the heart of heart disease and how your heart works and how it can go wrong and hopefully how we can put it right. The Naked Scientist comes to you from Cambridge University and is supported by the EPSRC, the STFC and Rolls-Royce. Until next time from me, Chris Smith, thank you for listening and goodbye.